Hi everyone, in this lecture I would like to discuss with you the theory of t-distributions. So the plan for this lecture is that we'll discuss the motivation and the history with a little bit of review of some of the crucial concepts of test statistics and their sampling distributions. We'll look at a worked example using table C with both hypothesis tests and a confidence interval. And then we'll use a bit of stata later on in the lecture, and I'll show stata's somewhat daunting output, although I've annotated every single piece of the output for you for your reference, but I'll also walk you through it in real time here. So here's an executive summary of t-distributions. It's concise enough to fit on one slide. So when we've been calculating test statistics for means in the past, we've been basically saying, I know this sample mean is drawn from a normal sampling distribution, which is at its heart just a probability density function, basically, or represented by one. So it's just that normal curve. And we can standardize it. We can take away the mean and then divide out by the standard deviation, and we'll get a score that is drawn from the standard normal. And remember that all we needed to do was to basically recall that the mean mu in this case is more often than not going to be hypothetical, and that the standard deviation of this sampling distribution is specifically a standard error, which is given by, in the case of means, and just one mean to be precise, because we'll see multiple means soon, sigma over the square root of n. Now, the problem is we oftentimes aren't going to know sigma, and so we'll estimate it with S, the sample standard deviation. And this should make a certain amount of sense, right? Why would we be doing inference on the population mean mu, so implying that we don't know it, but assume that we know sigma to be identical with any particular sample S? And further, what happens when S evidently varies in, say, two different samples from the same population from the same period of time, which would be the correct one to use? So we estimate sigma with S, but now we need to kind of account for that fact. And so far in my class, or if you've been following these lectures, when you have done that substitution, I've been telling you basically just assume that sigma and S are the same thing. So we have already been doing the correct procedure. We don't really have much of another way of coming up with an estimate of sigma, but we just now need to deal with the fact that it is in fact an estimate. What's the consequence? Our test statistic, t equal to x bar minus mu, that really should be mu naught, I'll fix that in a second, over an estimate of the standard error, has only a nearly normal distribution known as the t distribution. And today we will learn about that t distribution. Pardon me while I adjust my computer here. So the t-distribution looks a lot like the normal, but it's got bigger tails, or more uncertainty. The basic structure of our two procedures for inference, which are hypothesis tests and confidence intervals, will be totally unchanged, but the critical values for a given level of confidence or a given alpha, which again, those are basically complements of one another, are generally larger. Note that the t-distribution is actually a family of distributions. So normal curves have two parameters, mu and sigma, but the t-distribution has three parameters. It's got mu, sigma, and the degrees of freedom, which is noted df or nu. That's the Greek letter nu here. Even though it looks like a v, it actually makes the n sound. It's basically a lowercase n. And this is basically the pieces of information that are free to vary. So in this context, nu is equal to n minus 1 for the sampling distribution of a mean. We'll say more about degrees of freedom later. So first, let's introduce the t-distribution. So again, the concept here, just to reiterate, we almost never know the population standard deviation sigma, but we would need it to calculate the standard deviation of the sampling distribution of a mean, or the standard error. So as an approximation, we estimate it with the sample standard deviation S. That introduces another source of sampling error. So we have the sampling error associated purely with variation in the mean across the samples, right? But then we also have this other problem that we don't even know sigma, we're estimating it with S. So the sampling distribution then has what is known as a t-distribution rather than the normal distribution. The difference in practice is pretty minimal above n equal to 120, but you should know it in part because all statistical software in practice reports t-distributions or t-statistics and the like, and not z-statistics, even if they're almost functionally equivalent in most cases. By the way, here's a key idea. The rest of this course and the great majority of a lot of what comes next in statistics, maybe not the great majority, a giant share of what comes next in statistics can basically be boiled down to applying hypothesis tests and confidence intervals to situations where the standard error might change a little bit, The sampling distribution might change a little bit, but we're basically following the same logic that we've been learning for the use of z-statistics. So is that a bit dry? Yes, but it also means that what comes next is conceptually all of a piece. So let's look at the t-distribution. You may want to pause here and kind of see if you can figure out the difference. I'll actually say it out loud before I show all the text. So what I want you to note here is that here we've got two sampling distributions. We've got the distribution of a test statistic, where in the calculation of its standardized form, we basically use some known sigma. So this is from Larson and Marks, which is a great mathematical statistics textbook. And what the authors did was they basically simulated a bunch of draws from a known distribution where they were just able to input a true population standard deviation, and then they calculated basically 500 test statistics and plotted them, and then put the standard normal curve atop. You can see here that the standard normal curve is a pretty good fit. Then they did the same thing, but in each sample, and note that the samples are size 4 here because that's what's inside of the square root hat here, or the radical sign. They calculated the sample standard deviation, and then that was how they calculated the test statistic. Note that with this very small sample size of 4, so only 3 degrees of freedom, there's a bunch more information concentrated in the tails here. So that's kind of a visual illustration of the fact that associated with a t-distribution is much more sampling uncertainty when you have a small sample size. And I went ahead and calculated here just for us exactly how much information, just for point of reference, is concentrated between plus or minus 1 standard deviation of the mean. And in this case, here it's about 60% of the area under the curve only is between plus or minus 1 standard deviation on a t-distribution with degrees of freedom equal to 4. Now, this is not the true, basically, t-distribution, right? This is just 500 samples, so it's a large simulation. But if we did this basically a billion times or whatever, we would find when we took the area under the curve, or really, since that would be discrete data, we basically took all the heights and said that they asymptotically converge, we would see that it's 60%. So how big of a problem is this, right? We saw that it was a pretty big problem in the case of n equal to 4. But you may want to note that the t-distribution actually quickly approaches normality as a function of the degrees of freedom, nu, and recall in this context that nu is equal to n minus 1. You'll also often see degrees of freedom written df. Both are about equally common, so I'm going to switch between them. Sorry if that's confusing, but that's mathematical statistics for you. So the idea here is that, yeah, when we have degrees of freedom equal to 1, this would be a sample size of 2. This is visually quite different. But then when we get to 10, it's not too bad. And then when we get to degrees of freedom equal to 100, this is almost identical to the standard normal curve here. And you can play around with this if you like in Stata. It's not hard. It took me all of 2 minutes to put this graphic together. And you can mess with, any number of degrees of freedom. You could try plugging in 1,000, and you'll see that it's virtually identical to a degrees of freedom, a standard normal curve. So for n around 100, the approximation is pretty exact. Generally speaking, table A overstates our certainty by about 0.1%, so not really that big of a deal. For very large n, an exact critical t might actually be between the actual z-score and the table A rounded figure, so there's no net loss of precision. Now, what does that exactly mean? Well, you might know or you might not know that in table A we have rounding, right? So all those scores in table A are generally to the 100,000ths place. So they are rounded. And so for instance, the classic figure 1.9600 as the critical values that enclose in the standard normal, the middle 95%, is actually an approximation. It's like 1.9599 and then some other digits. But the point, this is actually really quite interesting, even though it deals with rounding, is that when we round that to 1.96, we're skipping over that distance, right? Well, actually, for very large n, say n of 200,000, which is like the sample size of a large sample such as the CPS, which is a very widely used sample, it's actually the case that the critical t values are between the true value, 1.959, blah, 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 for table A, and the rounded figure 1.96. And most people, we usually think about it like plus or minus 2 standard deviations is the rounded figure, 1.96 is the true figure for a z distribution. So almost no one ever pulls out the 1.959 blah 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 figure. If you're working by hand, it's considered very exact to use 1.96 because that doesn't seem rounded, but it is rounded. So if you were working by hand, this is my point, and you take you basically assume that you have a standard normal, and then you round and you use the figure 1.96. If you in fact have a very large sample and you should be using the t-distribution, the rounding is actually a better choice, ironically. Rounding to 1.96 is actually like a better choice. It's less imprecise than would be the mistake from using the exact figure when you really have a t-distribution. I guess I'm saying that in a slightly kind of long-winded way. Check the footnotes. This is hard to say purely with words. But basically the idea, to boil it down really simply, is that the amount of rounding error that is common in just using table A in situations where we should use some figure, that's exact to 100,000 decimal places or something, very often the error, quote unquote, used or caused by using those table A approximations is actually greater than the error than if we had a t-distribution with large N and then we just use table A instead. So basically the takeaway, long digression aside, is that this makes almost no difference with any appreciably large sample size. But since it is the more flexible and general form, this is how you'll always see things reported in actual statistics, so you do need to know that. So what really are degrees of freedom? You might wonder, and this is actually kind of a useful concept in general to know about. Generically, it's the amount of information that's free to vary in the solution of a problem given certain constraints. So practically, for a single standard score with unknown mean mu and unknown standard deviation sigma, degrees of freedom are given by n-1, where n is our sample size. But I did want to give a little bit more intuition for what these things really are. So note that what we're interested in here is the actual number of pieces of information that are free to vary when we estimate our test statistic. And one way to see this is to rewrite the t-statistic to pull out a z-score and write it as something times z-score. So we have t, which is lowercase here, but remember that it is a random variable. This is just a shitty part of mathematical notation, to be honest. We write it out like this. This is our test statistic. Then we can rewrite it so that we multiply sigma in the denominator by sigma in the numerator of another term, canceling them out. Then s is in the denominator of this other term, which would swap it out with sigma. That's just algebra. And what that means, we have here a z statistic. And then we have here the ratio of the true population standard deviation to the sample standard deviation. Z is a random variable, which is a function of x bar, so it's one random variable. It doesn't have any degrees of freedom in the same sense as does t, but in the denominator, we've got this x bar here, which is part of s, and it's something that we estimate in order to estimate sigma with s. So that kind of does two things. One, it gives this really kind of complex form, which turns out, fortunately, not to matter much, but it is the case that the t statistic, therefore, is a ratio of two random variables, and it has kind of a complicated exact expression. But secondly, it also means that we are kind of giving up one piece of information. You'll learn later on that there's an important kind of statistic known as the chi-square statistic, which again is quite complex in certain ways, but it's not hard to understand the basics of it. And it turns out that chi-square statistics differ when you have different degrees of freedom. So that's kind of an explanation for why we have in this t form, although we're meeting t first, the chi-square is the more fundamental form. We've got this sort of notion that when we have to estimate one piece of information, it goes away. It's no longer part of the kind of amount of information that we have that's free to vary. Here's another way to see it. So if I tell you, for instance, that there are 5 people on my pickup hockey team, and I tell you that in our last game, the team points per game, or the mean points per player, was 0.6, the total points scored by our team was 3. So the idea is we've got 5 people, the kind of average or the team points per game was 0.6, so that means that we had to have 3 divided by 5 to get 0.6, right? So that means that the sum of all players' goals must be 3, and that in turn means that once you know the team points per game and any 4 people's points scored, you know the 5th person's too. So if you know for sure that there were 3 points scored by the team overall, and you know that 4 people, for instance, had 2 goals among them, that means that the fifth person must have scored 1. Or if you know that 4 other people had 1 goal between them, that means that the last person must have scored 2. Or if you know that 4 people had 3 goals between them, the last person must have scored 5. The last person is variable, like it doesn't matter who it is, it could be any of the 5 people. But the point is that once you know 4 of the people, then you know the value of the fifth. So that's another way of saying that there is not really in that situation, once you fix the mean and you fix the n, there's not actually 5 pieces of information that are free to vary. There's only 4. So that's degrees of freedom, basically. Like that, in that scenario, degrees of freedom would be equal to 4 rather than 5. I'll say a little bit more at the end of this lecture more precisely about that, but I think that expresses the basic notion quite well. I wanted to give a little bit of interesting history about the t-distribution. So some early statisticians actually didn't really understand that there was a difference between these things, so who gets credit for the discovery that the t-distribution is a separate one? There's actually a guy called William Seeley Gossett who wasn't an academic, but he was a statistician working for Guinness, which is the same popular brewing firm that still exists today. You may have had their products if you're of the age of majority in your country. And yeah, they're a highly competitive brewing firm, and they had all these kind of small sample sizes. I think he was working with yeast samples in particular. And basically, Gossett just noticed that it turned out that with these really small sample sizes, when he had to estimate the population standard deviation sigma with S, that the theory wasn't working out. It was getting kind of close, but it just wasn't exactly correct, and it was consistently not actually correct. So he wrote an important paper called The Probable Error of a Mean, 1908, and he published it under the name Student because Guinness prevented employees from publishing under their own names. At least that's one version of it. There's some other versions of this story, but basically he had to use a pseudonym. And so he became known to history, at least for a long time, as Student. So this is why you'll sometimes see this referred to as Student's t-distribution. It actually has nothing to do with the fact that a student might use this. That's just Gossett's pseudonym, which is, possibly confusing thing. So how did this actually kind of get put into practice? Well, Gossett's discovery initially attracted very little attention. And by the way, this is all direct quotation from Larson and Marx. But 14 years after his publication, Gossett sent Fisher, who came up with a lot of the stuff we've been learning, a tabulation of his distribution and basically gave him a message in a bottle saying, no one gets me, man, but, maybe you'll understand this. So he basically just wrote this long shot letter to the most, probably the most prominent statistician in the world at that point. Certainly, in retrospect, one of the most decorated statisticians in history. And Fisher said, hey, great, no, you totally have hit upon something here that's not obvious and is quite important. So Fisher kind of more rigorously derived Gossett's probability density function. And according to Larson and Marx, he arbitrarily chose the letter T for this statistic. It's actually just that it's the test statistic as far as I know. And so this has become known to history as the student or student's T distribution. So that's that. Now, what's the point of this? Well, whether you're a responsible drinker or whether, like some people, you spent your formative years singing in a straight-edge grindcore band, may or may not apply to the person delivering this lecture. The point is that science receives a lot of stimulus from a lot of stuff that's not pure academic research, whether it's amateur aspirations, the go to the profit motive, or cooperative economics alike, accident, theological conviction shared by no one else living, which, a number of prominent scientists have held religious views that would seem to most people to be the height of superstition. Science is weird, it's fun, it's wacky, it is not the province of the experts. So I encourage you really to always keep these things in mind, that science is open to everyone. It's a contest of ideas. It is not a pecking order contest. This is just a fun picture of Homer Simpson because I love The Simpsons. Responsibly, no doubt, enjoying a couple of cans of Duff. Okay, so how do we actually use the t-distribution? Well, it's not too hard, although I want you to note that this table C here is actually something that works quite differently to table A. So you can read the description given up here, but I just want to show you live in real time how this works. So because the t-distribution is actually a family of distributions, we can't print, or it would be very prohibitive to print, a whole bunch of tables A for, A'1, A'2, etc., for all different values of t. So the way to kind of economize on this is basically what this table does is concisely give you a degrees of freedom. So you kind of look up your sample size here. Then a level of confidence, which corresponds to a two-sided t or p value here. And by the way, these p-values are really alphas. They're cutoff p-values. They're not actual p-values that you would get unless you happen to get exactly one of these test statistics, which is unlikely just by the laws of probability. The point is you then kind of look up, like let's say we want to do a two-tailed test with an alpha of like, let's say 0.05. So we would come down here and then we would look up in the table for our degrees of freedom. Let's say we happen to have a sample size of 25, so we would come up to 24. And we would see then that this is the critical value that is required. So we have to reach this value or exceed it in order to get statistically significant results. Sorry about that. With our given test statistic. So for instance, if we had a test statistic of 2 even, we would say that's not quite significant at the level of 0.05. Note that this is a table that basically is allowing you to draw conclusions. So it's not reporting actual p-values to you. Instead, what it's doing is giving you basically cutoffs, and that does sort of further ensconce a certain kind of way of thinking about these things where the key is to reject or accept rather than to report exact results, which is not a good thing in statistics, but that is the way that it works. And so we're going to use table C just for a little bit, and then we'll mostly default to using not table A, but Stata in practice, which reports exact p-values, which are more informative. But that's how table C works. Maybe at some point down the road, 10 years in the future or something, we won't even teach this table C anymore. It is a bit of an historical relic, but since it is useful to learn how to do these things by hand, so to calculate those test statistics by hand, it seems sort of artificial to calculate test statistics by hand, then use a computer to look up the exact p-values. So I'm showing you the pure by hand method for now, and then hopefully that helps you kind of understand the kind of pure mathematical basis, and then we'll use Stata later on. So here's the new procedures. Again, I just said these out loud, but basically calculate a test statistic or decide a level of confidence. And you really should decide an alpha too if you calculate the test statistic. Look up your n, then find the degrees of freedom. Then you want to look in the table to either get the critical value if you're doing a confidence interval, or see if you've exceeded it with hypothesis tests. Otherwise, this is pretty much the same exact stuff we've been doing. So let's proceed to an example. Here's a real-world example that I adapted basically by radically simplifying it, but it's kind of an interesting story. So U.S. academics and statisticians actually played something of a role in Bolivia's 2019 elections, which favored an avowedly socialist candidate, Evo Morales. Some people allege that small irregularities in the time it took to report data were suspicious, which has been a kind of hot topic in a lot of different places with elections recently. And you can kind of see the case either way. So it could well be the case that if different polling places have wildly different times to report, and we're not going to focus here on differences between polling places, by the way, we're going to just focus on the overall. But basically the idea is, if the time it takes to count votes differs radically from what you might expect, that could be evidence of fraud, but also it seems like there's got to be some error in the process. So this is a perfect case for an hypothesis test. So suppose that all parties agree that if the mean time to count votes across all polling places were only 23 hours, there is no fraud. Let's just suppose that's like a national cutoff. So our null hypothesis is that the mean mu hours to count is 23. Our alternative is simply that it's not equal to 23. Suppose we have data from n equal to 101 sampled polling places with the mean time across all 101 x bar equal to 24. Let s equal 8 hours and let alpha be conventional at 0.05. So would this be evidence against the null that mu is equal to 23? Let's conduct a two-sided test to be scrupulous. So we calculate our test statistic in the exact same way we've been calculating it for z-scores. So we would plug in 24 for our observed sample mean, 23 for mu naught, our hypothetical population mean. We would plug in 8 for our actual s, and here we're not even making any assumptions about its equivalence to sigma. That's just what s is. We'll deal now with the resulting uncertainty. And then we plug in the square root of n. In this case, that's the square root of 101. So we get a test statistic of 1.26 with degrees of freedom equal to 100. The results are not statistically significant. Let's take a look. So note here that we would come down to the row 100 because we have 100 degrees of freedom, 100 pieces of information that are free to vary here. And then we would look and see, okay, this is 1.984. This is where we would have to reach to get our cutoff. But we're actually between these two values here, 1.042 and 1.290. So we have a two-sided p-value between 0.2 and 0.3, which is much larger than our cutoff of 0.05. So we would fail to reject the null in this case. This is a picture of the sampling distribution under H0. Here we've got our standardized sample means. This is our observed test statistic 1.26, and then this is its counterpart. Notice that this is much larger than like an alpha of 0.05. You generally don't need to get p-values this way terribly often, again, because we'll do the whole test in Stata, but I just wanted to kind of show you what's happening here. What if you wanted to do a one-sided test because we were expecting that results would be higher? So in other words, test the alternative hypothesis that mu is greater than 23. The result is that it's still compatible with the null, but we look in a different place. So now, because we're doing a one-sided test, but we still retain our alpha of 0.05, we're actually going to look at this row here. And note, by the way, that these kind of all proceed like this because a one-sided p-value is basically going to be always half of the corresponding two-sided p-value because the distribution is symmetric. So here, we would only need to reach the level of 1.66 to have statistically significant results, but our test statistic is still languishing, between these two cutoffs here. So it's only significant at the level of, say, in this case, 0.3, which would be an absurdly high alpha that no one would ever use. So still compatible with the null, but we do evaluate it somewhat differently. Now, you may want to try to calculate a 95% confidence interval just to make sure that you feel comfortable with this. Note that our critical t we just obtained, it's 1.984, but if we hadn't already obtained it, you'd just go down the degrees of freedom rows to n-1 across the C columns to 95 and then find it. So what's our confidence interval? Hopefully you can do it by memory now. It's this here. But how did I calculate that? I took the sample mean, 24. I subtracted off the critical value, 1.984, times the standard error. And recall, well, don't recall because I didn't say it yet, but it's important to note that the standard error, we don't have a separate notation or way to describe the standard error when it's estimated or when it's known. If you look up the Wikipedia page, Wikipedia will say people use it both ways, actually. So we're going to continue calling that the standard error, but it is technically an estimate of the thing we had previously called a standard error. Again, mathematical notation is complete garbage. In a lot of other contexts, we make a big fuss about making it clear when something is an estimate or when it's a parameter. But here we don't do that. So sorry about that. But yeah, so the standard error is in this case just going to be 8, the sample standard deviation, over the square root of 101. So this is our confidence interval. The way to do it is given in the notes, but this should be wrote by now for everyone. So since the null value 23 appears in our confidence interval, it's possible that this is just random error. So this is exactly complementary to our two-tailed test, and it'll usually agree with the one-tailed one, but not always. If you're interested in the real story, you can see here, it turns out that US statisticians mostly got this wrong, unfortunately.
So now let's look at some Stata output for t-tests. The stuff we've gone over recently is mathematically intensive, but it's pretty light on code. Stata doesn't have easy Z procedures for means, since in practice it is very rare to know sigma, the population standard deviation. But T procedures are very common, right? And even though they don't make a lot of difference, we do just need to basically use those procedures in all but a couple of cases I'll address later when we use Stata. So sometimes it won't make very much difference at all, but we are going to need to do t-tests in Stata. Fortunately, they're very easy to conduct. But the sort of problem really is just going to be interpreting the fairly sizable amount of output. But we'll make sense of it all, I promise. Let's do it by hand first. So a motivating example, let's return to our lecture 17 example from the GSS. We were testing the claim that the mean number of pets was 1.5 in 2018 for US residents. So first, by hand, let's calculate, and then we'll use Stata. And then you might recall that this is what we did here. We were interested in testing the claim that the mean of pets in the population was 1.5. We used a conventional alpha of 0.05. We assumed that S and sigma were the same. And we found here a p-value. First, we found a z-score of 1.72 minus 1.5 over 0.009. We got, or a 0.09, sorry, and then we got 2.44. And then what we did, I've got this open in two browsers, was we used Stata to find basically a p-value that was about 0.01. So we're going to be more exact here, but we'll note that in the first case, we're going to get basically a test statistic that's identical. So what we would do is take away 1.5 from the sample mean, then divide by the standard error, which is the standard deviation in the sample, divided by the square root of n. Again, the reason for that is just that that's how the algebra of the variance of a sum of random variables works out. So we get this for our test statistic. Here I elected to be a little bit more precise with rounding. This is kind of a bad call on my end. Sorry about that, to have done lecture 17 without this level of precision. This is more mathematically exact. It really should be 2.45. But I don't want you to get the impression that that somehow changed. We were just a little bit inexact with rounding. The test statistic is going to be identical to how we calculated it before. Now we're going to go check table C though. So degrees of freedom in this case are 1146. We'll round down for the sake of modesty when working by hand. And generally speaking, you should just round all the way down to 1000 when working by hand. Sometimes that's going to be extreme over conservatism. But again, that's just what you should do when working by hand. Working by hand is intrinsically limiting. We won't often do it beyond this point. Okay, so what we do here is we go down to degrees of freedom equal to 1000. We locate the test statistic between 2.33 and 2.581. Then we find that it's located between a p-value of 0.01 and 0.02, same as we found before. Note here that our p-value is larger than it was, or it will be larger than it is for the Z procedure used in lecture 17. As I mentioned, I wasn't too exact with rounding in that lecture, but to demonstrate the point, I want to calculate the exact p-value from lecture 17. So what we should have done if we were being super scrupulous here, it doesn't make a huge practical difference, but because I'm demonstrating how these procedures differ, I want to be really exact about it. You can do it using the steps at right here, or you can just write the whole thing all in one go once you write some numpets. But basically, what all of this is going to do is to, let me open a new instance of Stata here. Why is this not? Oh, I've got this open. Sorry, folks. Stata is extremely good about not letting you close things. But generally speaking, if you try to quit without addressing, this is a good Stata note. If you try to quit Stata without directly answering the question about saving data, it'll actually go into this kind of like immunity mode where you then have to force quit it, which is pretty frustrating. Okay, so we'll use the GSS data here, and I'll show what I'm referring to. So let's just do, this code here. So we'll write some numpets and then this. So this would be our two-sided p-value that we should have gotten exactly by hand. Last time it's 0.0143, keep that in mind, because we're going to find that our p-value this time is a little bit different. So what does that output look like in Stata? I'll show you here, actually in Stata first, and then I'll switch back to the lecture slides since I just want you to be able to follow my annotations. So we'll come here, we'll say t-test numpets double equal to 1.5. And we get this output here. So this is the code to run this, but let's go back to the lecture slides just so you can see it here in a format where you don't need to constantly rerun the code every time you want to look back at this. So what's going on here? What does this tell us? Well, check out this handy annotated version on the next slide. So what's going on here? You can see my kind of somewhat sloppy hand annotations here. T-test is the command. We just write that. Then we write the name of the variable, two equal signs, because remember that double equal signs are required for evaluation in computers. Single equal signs are assignment. It does not make sense here to assign numpets the value of 1.5. We actually could do that. We could write replace numpets equal 1.5, but what that does is give everyone the value of 1.5, which we do not want to do. This here is our null hypothesis mean, or mu naught. In the output, Stata presents a lot of summary statistics in a somewhat confusing way. They really should swap the order of standard deviation and standard error. I don't know why they don't, but that's okay. It's not like wildly confusing, it's just aesthetically displeasing to me. So we've got the number of observations n here. We've got our observed sample mean x bar. That's the same as from the summary statistics. We've got the sample standard deviation here. Then we've got s over root n, or our estimate of the standard error. Again, sometimes people just call that the standard error. That's a case of mathematical notation being bad. That happens to be this quantity here. We've already found that once before by hand. Here is our confidence interval for the 95% confidence. So we have x bar plus or minus the critical t associated with 95% confidence, and also 1146 degrees of freedom, which I didn't have space to write in here, but technically you also have to specify which t distribution times the standard error. So that's just a bonus. It prints the confidence interval for you as well. So you don't have to do a separate command. We also get the t-statistic here. So note that this is 2.4482. We get the degrees of freedom nu, or n-1 here, which is 1146. It also shows us the null hypothesis in words too. I don't know why this is not like super important, especially this mean is equal to mean of numpets. It's just kind of wasted space there, but just so you know what all this is. Finally, the last bit, we get the actual conclusions, and this you want to pay close attention to. So the thing that we'll usually want to be concerned with is the alternative hypothesis that the mean is simply not equal to some value, because that's the more epistemologically conservative option, and what this gives us is our two-sided p-value, right? So we get our two-sided p-value. So you can read that here. It's a little bit tricky to figure out at first, but again, think about what this notation means. This is the probability that the absolute value of any t-statistic, so capital T, is greater than the absolute value of our observed t-statistic. So that means take whatever value of t you got, find the probability of values in that tail, and then the mirror image. That's what that ends up working out to. You can also just know that this means two-sided p-value, because working through the arithmetic of inequalities here is like kind of useful, but somewhat ancillary to our purposes. So this is what this is showing us. This is the sampling distribution of t-statistics under the null. These are standardized, so the mu is equal to 0 here, standardized t-statistics. And then we have here, well, by the way, I shouldn't say standardized t-statistics because they're already standardized, but standardized statistics, basically. I could have shown the original sampling distribution, but I thought that might be confusing. Technically speaking, you know, what we're doing with all this procedure is standardizing and finding p-values. That works out to the same thing as knowing information about the exact sampling distribution you have, but before computers got really good, that wasn't an option, so that's fine. Anyways, coming back to the main point here, we have the sampling distribution. It's centered at 0 here because it's been standardized, and it's got a standard deviation of 1 also. We've got our standardized statistic here. In this case, it was positive, so 2.45 with rounding here. But we've also got the area under the curve associated with the negative version of it, because note that this would be a case where the absolute value of t is larger than the, this shaded area is x values where the absolute value of little t is larger than the absolute value of some, big T is larger than the absolute value of our little t. So this area under the curve here adds up to 1.45%, or written as a decimal 0.0145. And we interpret that as this is the probability of sample means this weird or weirder to encapsulate both negative and positive, so far away from the mean. So saying big or small doesn't cut it because we want big and small, so we'll call it weird, given the null hypothesis. Here, this is the probability, this is, you know, the alternative hypothesis in the upper tail direction. This is the probability that a t-statistic would be this big or bigger. So we get sample means this big or bigger given the null hypothesis. Note that it's exactly half of this here. It won't always be exactly half, though. One of these things, either this or this, will always be exactly half, but it depends on which tail of the sampling distribution we are in. Note that this could be a little confusing here. You want to pay close attention to this because this large p-value is actually not good. You want to train yourself out of thinking habitually, oh, bigger, better, great. What this is actually telling us is we have very strongly insignificant evidence that the mean is less than 1.5 because we found a test statistic where we were much larger than the mean under the null. So the probability of a sample mean, quote unquote, this small or smaller, where this is actually quite large, is very big. We would almost always see values this small or smaller than it if the null were true. So we don't have any evidence that the null is smaller than 1.5. But you want to note very carefully the structure. Oh, by the way, this should be 0.9927. I'll fix that. Obviously, it should be. But you want to be very careful here because what this is telling you is, you can't actually draw a direct conclusion about this area up here. You'd have to run a separate test. All this does is tell you that you have no evidence against the null in the lower tail. And running another test, technically speaking, increases your probability of a type 1 error. So you want to be really careful about that and not kind of peek at the results post hoc. But yeah, that's basically the annotated stata output. I'll say a little bit more about matched pairs next time. Our book doesn't do a great job of clarifying what is or is not a matched pair, and it makes a lot more sense when we can contrast it with something that's not a matched pair, so we'll discuss this later. I did also want to briefly discuss degrees of freedom. This is optional. But I mentioned before that degrees of freedom are kind of this concept of pieces of information that are free to vary. Formally speaking, one way to think about it is that degrees of freedom are also the dimensionality of the vector space where a random vector lives. You can see previous discussion of this approach to the geometry of statistics in my last set of lectures. Remember that a vector is just a list of numbers, so if you have a list of all subjects' income or incomes in a sample, that's a vector. And the amazing idea here is that you can really conceive of the scores in this list as the coordinates of a line, or really like a ray, in n-dimensional space. So literally in the case of R2 and R3, or 2 and 3 dimensions, but metaphorically in the case of 4 dimensions and higher. Each axis represents a subject in that way of thinking about it. So this is our traditional way of thinking about things, right? We've got variables on the axes, and then this would be subject 2, this is subject 1. The dots or the points are individuals. But in linear algebraic ways of approaching statistics, we actually think about the axes as different subjects, and then this here is actually the vector x. It's the variable x represented geometrically, and this is the vector y. Okay, so how do degrees of freedom play out in this circumstance? Well, one very interesting idea that we've encountered before is that the sum of deviations about a mean is 0. So what that means is that the vector representation of deviations about a mean and a vector of those means, so a vector that's got the same score, which is a mean for every person, are orthogonal, and those that vector of deviations is also orthogonal to any scalar multiple of the one vector. That's what this means, the vector that's all one. So for instance, here's the vector 4, 4, but this is just a scalar multiple of the vector 1, 1. It's the vector 1, 1 multiplied by 4, where you multiply every component. So that's scalar multiplication, not matrix multiplication. So what this does is it actually cleanly partitions an n-dimensional space into 2 orthogonal parts, which is quite interesting, and we'll see that useful in a moment. Here to the right, you can see this is a vector of deviations right here. This is the deviation vector corresponding to the vector 7, 1. So if you break up the vector 7, 1, which has mean of 4, of course, into 2 orthogonal or perpendicular parts. Sorry, I was having trouble remembering the lower level version of orthogonal. Perpendicular parts, you would get basically a vector of deviations, so 3, negative 3, and a vector of means 4, 4. So this basically is a way of, and by the way, if you add these two things together, you'll get back the vector 7, 1. So for instance, if you take this here, you add it to the tip here, you'll come all the way out over to 7, 1. So basically these combine to produce the original vector. So what we're doing here basically is we're taking this vector in two-dimensional space and basically breaking it up into a vector that is comprised of two separate non-overlapping subspaces. So neither of them has any part in common. We can't go from any scalar multiple of this vector any way in the direction of this vector. Now let's think about that in a slightly higher number of dimensions, namely 3. So in this case, I have the same thing illustrated. I have the original vector 1, 2, 3. Then I have the deviations vector on that, which is negative 1, 0, 1. And those just come from subtracting off the mean, 2, from each point. So 2 less 1 is negative 1, 2 less 2 is 0, 3 less 2 is 1. And you can see that these are, again, orthogonal. It's a little bit harder to see because they're in three-dimensional space, but you can see that you could easily draw a 90-degree angle between them. And note that the dimensionality of a vector space is not given by the dimensions of the vectors in it, but by how many linearly independent ones span it. So again, we've got here to the right this vector of constants representing the means and this vector of deviations about them. And if we added them tip to tail, we would get the vector 1, 2, 3. But now, notably, we've got this kind of interesting fact here. So we've got this deviations vector here. Now, we've got a vector, an outcome vector, 1, 2, 3, that's in three-dimensional space. Note that the means are constrained to lie in a one-dimensional space. They always have to be along this vector of 1. So note that this is a scalar multiple of the one vector in 3 dimensions, 1, 1, 1. So we just multiply every component by 2, and we get the vector 2, 2, 2. Now, for a vector of deviations to be a vector of deviations, it must be orthogonal to this vector of constants. That's what it means for their dot product to be 0, and also therefore what it means for the deviations to basically add up to 0. The deviations add up to 0. So the idea is that this deviations vector and the constant vector, they have to remain orthogonal. So what does that mean about the space in which this vector lives? Well, it could be a lot of different things, but for this to be a deviations vector in any sense, so like once we say it's a deviations vector, it's got to be orthogonal to the one vector. So it actually can only lie in this plane here. It's a little bit hard to see, but you can kind of imagine like how, it could kind of go like out like this, or like down like this, or it could be oriented like this, and it could still be perpendicular seen from another angle if it's angled out like this. Like imagine it going out like this here, and there would still be a 90-degree angle kind of like right here, right? So imagine it going right out here, and you've got a 90-degree angle. It's not obvious from our orientation, but you can imagine kind of rotating the box and still seeing it. So basically, this vector is constrained to lie in a two-dimensional plane that is orthogonal to this deviations vector. So what that means is once we fix the mean, and this would be true in higher dimensions, it's a little bit hard to understand at first, but the idea is imagine all of this in 4 dimensions. Then we would have a 3-dimensional space that our deviations vector can lie in, even though the vectors are in 4 dimensions. And the idea is that it is that because we are constrained to still be perpendicular to that vector of constants, or that vector of constants. So it's a little bit hard to see in these like higher dimensional spaces, but you can sort of see it here. Once we basically fix some value of the mean for a bunch of observations, then that puts a constraint on the actual scores, like the deviations about them. And this is a little bit different because what we've been saying before with degrees of freedom is, well, once we know the mean and then the value of like 5 subjects on the mean, or 4 to use my previous example, then we know the value of the 5th subject. So we were kind of thinking about it like once we fix n-1 pieces of information, then we know the final nth piece of information. This is a different perspective, but it's the same idea. Now we fix, instead of like one person's score here, we fix one dimension of everyone's score. So in other words, we fix this dimension. We have to remain like, we have to have a, if we're basically thinking about it like this, we want to put out a deviations vector, right? That means that it's got to be orthogonal to this. So this represents basically a bunch of information about the scores, but that information always has to remain orthogonal to one dimension of the space because it's a vector of deviations, right? It's part of a vector that when added to a mean will give some other vector that we started with. So for that to be the case, this has to be orthogonal to this here. And so again, what that means is that this lies in a space that is actually one fewer dimensions. It can't be like this because then it is not orthogonal to this vector in any way. It can't come out like right out here because there's no way in which it is orthogonal to this. That means it wouldn't be a vector of deviations. It doesn't actually add up with this to give a vector that's got this as a mean. So the idea here is once we fix a particular mean and then we say some other vector is deviations about that mean, that other vector has to be orthogonal to this. And then again, you can see this is a vector in 3 dimensions, but it's actually got to stay on this plane. And that means that it has one kind of less, piece of information, basically. So even treating this as a random variable, it's a random variable with that constraint. That's all I got. Thanks for watching.